So today we are going to discuss about the two-body center force problem and reduction of that two-body center force problem to one-body problem. And for that, let us consider two particles which are of mass m1 and m2 and which have position vector r1 and r2. And let's consider that the position of m1 with respect to m2 is equal to r, and from triangular law of vector addition we can say that vector r is equal to r2 minus r1. Okay, and we can consider that equation and we can write it as r2 minus r1 is equal to vector r as our equation 1. We already know the equation for Lagrangian, right? How to find the equation for a Lagrangian? It is equal to L is equal to T minus V. So the equation for Lagrangian will become L is equal to T minus V, and from here we can say that what is T and V, right? What is T and V then? T will be equal to, there will be two masses m1 and m2, and there are two vector formulas which are there are two position vectors which are r1 and r2. So our L will become half into m1 r1 dot square plus half m2 r1 square minus P of r. Okay. Now let us consider another point here, that if we consider the center of mass of these two objects, that these two masses, that is m1 and m2, as exactly the midpoint of these lines, and if we represent it as Cm, if for Cm means center of mass, if we consider this center point as Cm, and let's consider the position vector of this as, let's consider that as capital letter R. Position vector of this is capital letter R. So from the definition of this position vector, we can write the value of position vector R as capital R as m1 r1 plus m2 r2 divided by m1 plus m2. This is our equation number 2, and this is our equation number 3. So only from our equation 1, from here we can write as, we can give the value of r2 as, from here we can find the value of r2, right? What will be the value of r2 from this equation? r2 minus r1
r plus r1.
vector r. Yes, it will become, from this we can write vector r2 as vector
r2
r plus vector
r1.
r1. So we will substitute that value, we will consider this as equation 4, and we will put this value, the equation 4, in our equation 3, which is this one. So we will substitute that. So if we substitute that, we will get r is equal to vector capital R is equal to m1 vector r1 plus m2. Instead of r2, we will be writing as
R
vector
plus
r plus vector r1. So m2 into vector r plus vector r1 divided by m1 plus m2. So from here we can take this m1 and m2 to this side, and we can also remove the brackets and expand this, so it will become capital letter R into m1 plus m2 equal to m1 vector r1 plus m2 vector r plus m2 vector r1, right? From here what we will do is, here we have common r1 and r1 in both m1 and m2, right? So we will take this r term, vector r term to the left hand side, and we can write that as r into m1 plus m2 minus m2 vector r is equal to, we will take r1 common, so we can write as m1 plus m2 into vector r1, m1 plus m2 into vector r1. So if we look carefully, in this both left and right side there is one common term which is m1 plus m2, right? So we will divide the whole equation by m1 plus m2. So if we divide this whole equation by m1 plus m2, we will get here, this will be cancelled out and it will be r minus m2 vector r divided by m1 plus m2, which will be equal to, this will be cancelled out,
R1.
r1, right? Now if we take time derivative on both sides, we will get r1 dot, note that one first. So r1 dot is equal to, vector r1 dot is equal to vector capital letter R minus m2 by m1 plus m2 r1. We will get this as a equation. So we can consider this as equation number 5. Okay. So similarly, if we put from here we find out the forward the value of r2, right? Similarly, from this equation we can also find the value of r1, right? It will become r2 minus r1. So writing this part. From that equation we can write vector r1 as, vector r2 minus vector r. Okay, so we will substitute that also in the previous equation, which is r is equal to, capital letter r is equal to m1, instead of r1 we will write as r2 minus r. Plus m2 vector r2 divided by m1 plus m2. So here also we will expand this and we will take this to left side. We can write as r into m1 plus m2, and if I expand it here, we can take this m1 r2 this side, because r2 will be common here. So I am taking that directly and reducing one step here. So we can write m1 vector r is equal to m1 plus m2 here. R2 is common, so we can write as m1 plus m2 into vector r2. So if I divide both of the sides similarly, like plus by m1 plus m2, we will get as
R is equal to
r
minus m1 r by m1 plus m2 is equal to r. R.
Okay. Similarly, we will take time derivative like we did here on both sides. So we will get it as r2 dot is equal to, vector r2 dot is equal to capital letter r dot minus m1 by m plus m2 into So this will be our equation number 6. Okay. So there are two equations which are with one is of R1 and one is of R2. So we will consider both of this equation and we will put that in our Lagrange equation. Okay. So we will put this R1 and R2 in the Lagrange equation. The Lagrange equation will become half into m1, because R1 square m1 R1 dot square. Instead of that, we will write it as what is the value of R1 dot here. We will substitute that here. It will become capital R dot minus m2 by m1 plus m2 into R dot whole square minus another one which is not minus plus half m2 into R dot plus m1 divided by m1 plus m2 R dot whole square. And to find Lagrange, we not only need P, you also need R, the potential energy, right? So here we will be with respect of mass, all these are with respect of R. We can write it as V of R. So this will be our Lagrange equation. So if we see carefully, this is the form of A minus B whole square, right? And this is the form of A plus B the whole square. So what we are going to do is we are going to expand these equations. So when we expand, we will get L is equal to half into m1 capital R1 square plus m2 square dot R1 square. If this becomes square, we don't need to put the vector value. So it will become R1 square divided by m1 plus m2 whole square minus 2 into vector capital R m2 R dot divided by m1 plus m2 plus half into m2 R dot square plus m1 square R dot square divided by m1 plus m2 plus 2R m1 R dot divided by m1 plus m2. So, and we have that V of R minus V of R. So, from here, so if we take this m1 to inside this bracket and m2 also to inside the bracket, we can write the equation as from this whole part. So if we take the m1 and m2 inside, we can write the equation as L is equal to half into m1 r dot square plus m1 m2 square divided by 2 m1 plus m2 square r dot square minus m1 r dot m2 r dot divided by m1 plus m2 plus half into m2 r dot square plus m2 into m1 square divided by 2 m1 plus m2 whole square into r dot square plus m2 r into m1 r divided by m1 plus m2 minus p of r. So from here we can see that this term and this term both are similar. As this is multiplying, these both terms are similar, so we can cancel both these terms and we can write it as L is equal to, here we have r dot square common in both of these terms, so we can take it as common. So half into m1 plus m2 r dot square plus here also in the second term also there is m2 square and there is m1 square. So if we take that common, we can write it as plus m1 m2 into the first term here is m2, so we can write first as m2 plus m1 divided by 2 into m1 plus m2 whole square. So here is m1 plus m2, here is also m1 plus m2. We can cancel one of these terms, and here also there is r whole square minus v of r. So we can write it as L is equal to half into m1 plus m2 r dot square plus half into m1 m2 divided by m1 plus m2 into r dot square minus p of r. Okay, so from here we can write this m1 plus m2 as capital letter. Okay, capital letter means the whole mass, so we can write this term as capital letter M, and also we can write this m1 m2 divided by m1 plus m2 as mu. We can write this term as mu. So what mu is? It is the reduced mass of the system. This is the reduced mass of the system, and this is total mass of the system. So if we substitute that value, we can write it as L is equal to half into m r dot square plus half into mu r dot square minus v of r. Okay, and as in the case of center of mass, it will be both in tendency of it will be constant motion or uniform motion, or it will be rest. So the value of r dot will be, the value of a constant, right? What is the difference? If we take the derivative of a constant, it will become 0, right? So as the center of mass is at constant rest, so constant motion, we can take the value of r dot as 0. Okay, we can take this value. This as 0. Okay, so this whole term will become 0. So we can write our final equation of Lagrangian as L is equal to half mu r dot square minus b of r. So this is the equation for a two body central force problem, which is converted or reduced into one body problem.